Hello, I'm Phil Rennert, and I'm going to show you a possibly surprising fixed point theorem in a simple way using 2 sheets of paper. Along the way, we'll see some unusual things. We'll go through an existence proof of the fixed point, but those are never fully satisfying, so we'll look in detail at what's really happening. We'll discover how something that sounds impossible turns out to happen. We'll end with a fundamental difference between polar and rectangular coordinates. To start with, we have 2 sheets of paper. Bottom and top, which we'll assume are identical, at least for the moment. Let me switch to top view. So here we are with bottom and top. We define the function same from bottom to top, where each point on the bottom maps to the same point on the top. If I hold the top sheet over the bottom, all mappings of same go straight up. I'm going to be using descriptive function names, as in computers, rather than single letter names, which are usual in math, because I hope this makes for easier understanding. So same is a plain and simple mapping from bottom to top. Our second function is not so simple, and it's called crumple. It maps the top sheet into 3-dimensional space, and it looks like this. Now, I'm not going to try to write equations to describe crumple. But notice that crumple is at least continuous. I didn't cut the paper or stretch the paper. So here is the crumpled top sheet sitting on top of the bottom sheet. And one more function, project, which maps the crumpled top sheet back down onto the bottom sheet by going straight down. For each point on the top sheet, imagine poking a needle vertically through it, and the image is the point on the bottom sheet it hits. Okay, 3 functions, and here's a summary. And we're going to put them together to make a function from the bottom sheet to itself, like this. For each point on the bottom sheet, go to its image under same on the top sheet, then go to that point's image in 3 space under crumple, wherever that is, then project straight down to return to the bottom sheet. And we'll call this function 3-step, which maps every point on the bottom sheet to a point on the bottom sheet. So this is the formal definition for any point P in bottom. 3-step of P is you start with same of P, and then crumple that, and then project that. A composition of 3 functions. Now, note that 3-step maps the bottom sheet to a subset of the bottom sheet. I'm going to draw a curve and call it C. This curve C surrounds the crumpled top sheet, and you can see that every point on the bottom sheet gets mapped to a point in the interior of C. Another way to think of the 3-step function is as a vector field. I'll call this function vector field. For each point on the bottom sheet, the foot of the vector is at that point, and the head of the vector is the point 3-step maps it to. For instance, maybe the vector at this point has its same point somewhere like here, so it gets projected down to here, and the vector goes from here to here. And here is a statement of vector field. Okay, now we're ready to state our fixed point theorem in 3 equivalent ways. 1. There is some point in the bottom sheet whose same point in 3 space is sitting directly above it in the crumpled top sheet. Or 2. The function 3-step has a fixed point. There is at least one point in the bottom sheet such that 3-step of that point equals that point. So 3-step fixes that point. By the way, this doesn't mean the point is broken. The root word is affix, meaning to put in place. Or 3, there is at least one point on the bottom sheet where vector field has 0 length. So these are 3 ways of saying the same thing, and all 3 are true or false together. It's interesting to note that this claim applies to any crumple function. So if I crumpled slightly differently, and I don't think I could duplicate this particular crumple again, the theorem is still true, though probably with a different fixed point. Yet a fixed point always exists. That's the theorem. Now, it will be important that 3-step is a continuous function, by which I mean if we have a point on the bottom sheet and we draw a small circle around it, then the images under 3-step of that circle on the bottom sheet will all be within a small distance of the image of the original point. And the same for any small distance in the limit as distance goes to 0. Why is 3-step continuous? Well, it's composed of 3 other continuous functions. Clearly, same is continuous. The image of a small circle in bottom is exactly the same circle in top. Crumple is also continuous. The crumpling process can never move 2 points farther apart, and may make them closer if there's a crumple between them. And project removes one dimension from 3 space in projecting down, so it also can only move 2 points closer or leave them the same distance. If the image of a circle in bottom gets turned almost vertical in the crumpling process, then project may move 2 points very close together or even on top of each other. So project is also continuous, and so is 3-step. And similarly, so is vector field. Given a point P in bottom and a small circle around it, the heads of all the vectors in that circle lie within the same small circle around the head of the vector at point P. We need one more tool, and then we can begin the proof. I'm going to remove the crumpled top sheet for the moment. For a closed curve like C and vector field, we define cycle number as a function of the curve, like so. We start at any point on the curve, and we look at the direction of vector field. Maybe it's like this. And we move around the curve, watching how the direction of vector field changes. And as we go clockwise, one circle around the curve C, the question is, how many clockwise cycles did the direction of vector field make? Well, let's compute it for this curve. Since the image of the bottom sheet under 3-step lies inside C, and so the heads of all vectors in vector field lie inside C, then the direction of vector field along C is always inward. It may waver back and forth a bit as we go around. We don't really know, but it always points in an inward direction. So as we move around the curve C, the vector direction makes one clockwise cycle. So cycle number of C equals 1. And since we return to the starting point on any closed curve, cycle number must always be an integer. It can't have a fractional part. Now, not all curves have cycle number 1. For instance, look at this curve. Which contains none of the images of the bottom sheet under 3-step. So, the direction of vector field everywhere on this curve is confined in a fairly narrow angle between maybe here and here. So as we go around this curve, the direction of vector field must always point kind of in this direction. It may waver back and forth, but there's no way it can make a full circle. So the cycle number of this curve is 0. All right, let's begin our proof. This will be a proof by contradiction. If the theorem isn't true, there is no point of bottom where vector field vanishes. Then there must be a minimum length greater than 0 for all vectors in vector field. Since vector field is continuous on a closed set, it can't get arbitrarily close to 0 without being 0 at some point. So vector field has a minimum length on the bottom sheet. I'll call that min. Now one more idea. I want to pick a center point inside C and call it center. It doesn't have to be in the center. In fact, I'll draw it well off center. But all I need is that it has a line of sight to all points along C. Now I'm going to rename C as C sub 1. And define a family of curves C sub alpha, for alpha between 0 and 1, like this. For every point on C, draw the ray from center to that point. And then go out along that ray a distance equal to alpha. So C sub 1 is just C, because you go all the way out to that point on C. C sub 0.9 is 9/10 of the way out from center to the curve. And C sub 0.5 is halfway. I'm going to attempt to draw C sub 0.5 by going halfway out by eye. Looks like a point here. Maybe a point here. Point, say, here. Maybe a point here. And here. And here. And here. And here. So we get a curve that looks like this. This is C sub 0.5. So imagine this family of curves starting at C1, the original curve, and then shrinking down from C sub 1 toward the center as alpha decreases from 1 toward 0.